Continuity. In everyday speech, continuous means having no breaks or interruptions. Informally, we can ask ourselves, can I draw the graph of this function without ever lifting up my pencil? So we have some examples of continuous and discontinuous functions here. So this first function is continuous. I can draw it without ever lifting up my pencil. Same thing with the second function here. But the third function is discontinuous at the x value 2. That's where I'd have to jump up and continue on with the graph, but I'd have to lift up my pencil at 2. And over here at 3, I also am discontinuous because I'd have to go down here to complete this point and then continue on. Continuity at a number c. So now let's go ahead and suppose f of x is defined on some open interval containing the x value c. Then we would say f is continuous at x equals c if all three conditions below hold. So the first thing we need is f of c to be defined. We need the limit as x approaches c to exist. And we need the limit as x approaches c of f of x to equal f of c. So this last one means the limit has to equal the function value. So if we take a look over here, is f of x continuous at x equals c? So we can see that the graph is not continuous at c, but the part that's missing from the conditions is f of c isn't defined. So I don't have f of c defined in this first example. In the second example, well, f of c is defined, but the limit doesn't exist, so part 2 is violated. And in this example, no, I'm not continuous. I am defined, and my limit exists. So I do have both conditions 1 and 2 satisfied, but the limit doesn't equal the function value. So this third example doesn't meet condition 3. But this last example, yes, we can see that we're continuous, but precisely we can see the function is defined, the limit on both sides exists, and the limit equals the function value. So we need all three pieces to be continuous at a particular point. Discontinuity. If a function f is not continuous at c, we say that f is discontinuous at c, or f has a discontinuity at c. Informally, a discontinuity is a break or an interruption in the graph. So one of the types of functions that can be discontinuous is a piecewise function. So is the following piecewise function continuous at x equals 2? So here's my piecewise function here. And then we're going to graph it to verify our answer. So we're going to go ahead and check what the three conditions. First is f of 2 defined. So I'm going to go up here to my piecewise function. We're switching between the two functions at the x value 2, but specifically at x equals 2, I would substitute 2 into the first part of my piecewise function. So yes, f of 2 is defined. I would plug 2 into the top part only, and I would get f of 2 is equal to the square root of 2 plus 2, which is the square root of 4. So I get out to the value 2. So yes, f of 2 is defined. So the second thing we're going to check is whether the limit as x approaches 2 of f of x exists. So we have to check both the limit from the left and the limit from the right hand side. So the limit as x approaches 2 of the left hand side of 2 means we're going to go ahead and use the top function. So the square root of x plus 2. So I'm going to have to figure out whether or not this limit exists from the left-hand side. Now, we will discuss this in more detail, but what we are allowed to do is direct substitution onto this particular type of equation. So if I directly substitute in 2, I would get the square root of 2 plus 2. So I would get out, again, the square root of 4, which is 2. That's the limit from the left side of 2. And then I would figure out the limit from the right side of 2 as x approaches 2 from the right. Well, that's x values greater than 2 over here, so I'd use x minus 5 this time. So x minus 5. And we can go ahead and substitute 2 into the value of x over here. And 2 minus 5 is going to give us negative 3. So part 2 is not satisfied. So f of 2 is defined, but the limit does not exist. These two values are not equal to one another. So the answer is no, the piecewise function is not continuous at 2, it is discontinuous at 2. So I'm going to go ahead and put discontinuous at x equals 2. And then I'm going to go ahead and graph the piecewise function. So the square root of x plus 2, that's going to be the square root of x function shifted to the left 2 units, because I'm adding 2 to the x value here. So that means it's going to start over here at negative 2. And we know that at 2, 2, let's see, that's where the function value is defined. So my square root function looks like this. So I start at negative 2, I look like the square root function just shifted to the left 2. And then x minus 5 when x values are greater than 2. So when x values are greater than 2, well specifically at 2, I know I'm down at the y value negative 3, but I have to be an open circle there. And then I have a slope of positive 1, because this is a linear function, x minus 5. So up 1 over 1 means that I'm going to look like this to the right of 2. So I can see that my function is discontinuous at 2. So it's obviously a lot easier to see on a graph, but there's also an analytical way to check this by checking if f of 2 is defined, by determining if the limit exists with the technique here that we went ahead and practiced, direct substitution. I can go ahead and plug in the 2. I can go ahead and plug in the 2, but I got 2 different values out. So if the limit from the left doesn't equal the limit from the right, the two-sided limit doesn't exist. And then there's no need to check condition 3 if one of the first 2 conditions fails. Now let's look at the types of discontinuities. We can have removable, or what we call point discontinuities, and this occurs when the limit exists, but f of c is either undefined or the limit doesn't equal the function value. So in that case, we say f has a removable discontinuity. So both of these are examples of that. So the limit is defined, but on this first one, it doesn't equal the function value. And in the second example, f of c isn't even defined. The next type of discontinuity is infinite. So if one or both one-sided limits does not exist or is infinite, then we say f has an infinite discontinuity. So here at 0, I would have an infinite discontinuity because both sides go towards an infinity. And over here at negative 2, I would have an infinite discontinuity because one side goes toward an infinity, goes towards negative infinity. So it could be both or one side. Moving on to a jump discontinuity. If the limit from the left and the limit from the right both exist at x equals c, but are not equal, then we say f has a jump discontinuity at x equals c. So both limits from both sides of 0 exist, but they're not equal to one another. So we say this is a jump discontinuity. So this piece over here completely jumps up to a different function to the right side of 0. Finally, we have an oscillating discontinuity. If the function oscillates too much near c, that's when we say f has an oscillating discontinuity. So what that means is that it just jumps back and forth too much. The y values don't get close to any one particular value. So as I'm approaching 0 here, it's just going crazy. And I can't narrow in on one particular y value. In this example, we're asked, how would you define f of 3 in a way that makes f of x equals x squared minus 5x plus 6 over x minus 3 continuous at x equals 3? This is called removing the discontinuity. So we're essentially told that at x equals 3, I'm not a continuous function. And we want to figure out how would we define 3 so that we do have a continuous function. So if I think about what happens when I plug in 3, some students will say, oh, there's a vertical asymptote, because they think about, okay, I can see plugging 3 into the denominator will make the denominator equal 0, and that's where vertical asymptotes occur. But we really have to be careful. Vertical asymptotes only occur in x values where it makes only the denominator 0. If the numerator and denominator are 0 at that x value, then it turns out we have a hole in the graph. And that's exactly what happens on this rational function. So to figure that out, to see that more clearly, we'd have to factor the numerator. So if I factor the numerator here, it factors to x minus 3, x minus 2, over x minus 3. So this is equivalent to x minus 2, except not at x equals 3. So at x equals 3, there's a hole in the graph. There's a hole at the x value, positive 3. So what we need to do is figure out, essentially, how to plug the hole. That's how we make a function like this continuous, if we plug the hole. So if I think about the graph of x minus 2. So x minus 2 is a linear function. It has a y-intercept of -2 and a slope of 1. Right? So my slope is 1, my y-intercept is -2. So I'm going to plot that point. This would be at 2. I'm going to go ahead and draw my line here. But the actual function f of x, it has a hole in it at x equals 3. So at x equals 3, there's actually a hole in the graph. So I need to figure out exactly where that hole is. What is that y value? And if I figure out that y value, that's what to define f of 3 as. So I need to figure out, well, what's that y value? So it's actually pretty straightforward. This line was x minus 2. So how do I find out where that hole in the graph is? I simply plug 3 into x minus 2. So if I plug 3 into x minus 2, then I find out that that y value is positive 1. So I would just take that number, x equals 3, and substitute it into the x value, or values potentially, that are remaining after canceling out the linear factor x minus 3. So plugging in 3 guaranteed me that that y value was 1. So how would I define f of 3 so that I actually do have a continuous function? I would define f of 3 to equal positive 1. So I would define f of 3 to equal positive 1. Or now, a more formal way to maybe write this function would be f of x is equal to x squared minus 5x plus 6 over x minus 3 when x is not equal to 3. And we're going to define it as 1 when x is equal to 3. So that's kind of a little bit more formal of a way to express or how to create a continuous function from the given rational function that was provided. But essentially we were asked just this part here. F of 3 would have to equal 1 to remove the discontinuity. We also have the notion of one-sided continuity at a point. So a function f is right continuous at x equals c if the limit as x approaches c from the right of f of x equals f of c. So basically it ends with that filled in circle from the right hand side. So the right-sided limit equals the point, equals the function value. And I'm left continuous as I approach from the left side of c if I equal the function value. So it ends with, again, a filled in circle from the left-hand side. So if I take a look at this graph right here, just as a quick example, at 2, I'm discontinuous, but if I want to break it down, I would say that there is one-sided continuity. I have a left continuous value at x equals 2. So this graph that's shown here is left continuous at x equals 2. In this example, we're going to look at the graph shown and state each value where f is discontinuous, what's the type of discontinuity, which continuity criteria fails there, and then determine whether I'm left, right, or neither at each value. So at the first x value, starting from the left-hand side, I have a discontinuity at x equals -1. The type of discontinuity, since one side, the right-hand side, is going towards -infinity, I have an infinite discontinuity. It's important to know I can't be both an infinite and something else, so sometimes students want to put this as a jump discontinuity, but it isn't, because a jump discontinuity requires both limits from the left and the right to exist, and the limit from the right doesn't exist, it's infinity. The continuity criteria that fails is that the limit from the left doesn't equal the limit from the right. So the function is defined up here, but the limit from the left side of -1 doesn't equal the limit from the right side of -1. And am I left continuous, right continuous, or neither? At -1, from the left-hand side, I end at the filled-in circle, so I am left continuous. The next x value that I'm discontinuous at on this graph is x equals 2. So x equals 2. The type of discontinuity this time is a jump discontinuity. So the limit from the left exists, the limit from the right exists, but they do not equal each other, which is the continuity criteria that fails. So actually, there's more than one that fails. So the function isn't defined. So I have that f of 2 is undefined. And really, I can stop right there. But I could also have listed that the limit from the left doesn't equal the limit from the right. And then finally, I'm neither left nor right continuous at 2. So from both sides, I end in an open circle. The next x value I'm discontinuous at is +4. Once again, I have a jump discontinuity at +4. And the criteria that fails, this time we are defined at 4, but the limit from the left doesn't equal the limit from the right side of 4. And finally, at x equals 4, am I left continuous, right continuous, or neither? I am left continuous. So as I get close to 4 from the left, and I want to start just barely to the left of 4. So sometimes people want to start way over here and they confuse themselves. So you want to look at a little tiny interval around 4. So from the left of 4, I end at a filled-in circle. So I am left continuous. I am next discontinuous at x equals 5. As I can see, I'd have to lift up my pencil here. The type of discontinuity is removable or a point discontinuity. So I'm going to go ahead and write removable. You could write removable or point. You don't have to write them both. The criteria that fail. So the function is defined at 5. It's defined down here at -2. The limit does exist at 5. Both sides approach -1. So it is the third criteria that fails. The limit as x approaches 5 of f of x doesn't equal the function value f of 5. And on this one, I'm not left continuous or right continuous. From both sides, I approach an open circle. So I am neither. And finally, I'm discontinuous at x equals 7. The type of discontinuity is again removable or point discontinuity because the limit from both sides does exist, but the function value isn't defined there, so that answers continuity criteria that fails. The function is not defined at 7. F of 7 is undefined. And I'm, once again, neither left nor right continuous. So both sides from the left and the right-hand side end at an open circle. The last part of this example has us find all intervals where f of x is continuous. So we're going to describe these intervals as x intervals. So we're going to focus on the x-axis and describing where I have a continuous function. So I'm going to start on the left-hand side. at negative infinity, since this arrow is pointing to the left, I'm going to be from negative infinity all the way till negative 1. And since at negative 1 I end at a closed point, I'm going to include that value in my interval. So the first interval is going to be from negative infinity to negative 1, and I'm going to include a closed bracket because I end at a filled in circle. And then we're going to move on to the next interval where f of x is continuous. So we're describing all the pieces. This is a complex looking piecewise function. We're going to describe each piece that can be drawn without lifting our pencil. That's essentially what we're trying to describe. So right after negative 1, I have a continuous function all the way up until the x value 2, where I'd have to lift up my pencil. So I can't actually put my pencil down at negative 1, so my next interval is going to have open parentheses, negative 1. I'm going to extend all the way to positive 2, but also have an open parentheses because I can't officially put my pencil down at 2 either. So both sides of the interval are open parentheses. The next piece of my piecewise function extends from the x values positive 2 to positive 4. But at positive 2, I have an open circle, so I have to have an open parentheses. And at the x value 4, my piece of the function ends at a filled in circle, so I will have closed brackets. So I have from positive 2 all the way to 4 closed bracket. And then I have a small piece to my function here where I'm continuous from 4 to 5, not including 4 and not including 5. So that would be open parentheses 4, open parentheses 5. And another similar interval extending from 5 to 7. I can put my pencil down all the way from 5 to 7, but not at 5 and not at 7 specifically. So open parentheses around 5 and 7. And then finally, from 7 on to positive infinity, I could keep my pencil down the whole rest of the time. So not at 7 though. 7 is an open circle there. So I would have the last interval as open 7 and then all the way to infinity. And infinities always have open parentheses. We're going to define a continuous function as one that is continuous on every point on its domain. So we're clearly not going to take a function and check every single point on its domain. And there are some functions that come up a lot more often than others that we know are continuous functions for every point in their domain. So this list of functions, polynomials, nth root functions, rational functions, trigonometric and inverse trigonometric, exponential and logarithmic functions, we know that these are continuous functions for every point in their domain. So it's the only part that we really need to check and verify is that we are picking a specific point in the domain of these types of functions. Next, we have a really important theorem. It says that if a function is continuous at a particular value, x equals c, then the limit is equal to the function value obtained by direct substitution. So essentially, the limit as x approaches c of f of x is simply equal to f of c. And this only works, we can use direct substitution, if f of x is continuous. So in this limit, we have evaluate the limit as x approaches pi over 2 of cosine x. So now we know cosine x is continuous on its domain, which is all real numbers, and pi over 2 is a number. So in order to evaluate this limit, we can now apply direct substitution. I can simply take pi over 2 and plug it into cosine to obtain cosine of pi over 2, which is, of course, 0. So this is a really powerful tool for us to evaluate limits, provided that the function here is continuous. In this example, we want to find the value of k so that f of x is continuous everywhere. So x minus k, where x is less than or equal to 1, and x squared plus 2 when x is greater than 1. So I know that I have a linear function here and a quadratic function. They're both polynomials. They're both continuous on their respective domains. So the first domain is x less than or equal to 1. The second restricted domain is x greater than 1. So the only place we're potentially discontinuous on this piecewise function is at 1. I might jump from one function to the other. So I want to force this to be continuous, so I need the limit from the left side of 1 to equal the limit from the right side of 1. So we have the limit as x approaches 1 from the left of x minus k that has to equal the limit as x approaches 1 from the right of x squared plus 2. So we're going to go ahead and use direct substitution on this. We are going to substitute 1 into each x. We're going to force these two sides to be equal to one another. So if I substitute in 1 into this x, I end up with 1 minus k on the left-hand side has to equal, plugging in a 1 on the right-hand side, 1 squared plus 2. But here, now I wanted to find that value of k, so I'll solve for it. So here I have 1 minus k is equal to 3. If I subtract the 1, I get 2. Divide by the negative, I get k is equal to negative 2. So that is the value of k that will make this piecewise function continuous. And if you wanted, you could also graph if that helped verify the information for you, or plug negative 2 in and check the 3 conditions. The function is defined, the limit exists, and the limit equals the function value. We have some laws of continuity that are really going to help us out now that we have a list of known continuous functions. If we assume that f and g are continuous at x equals c, then the following functions are also continuous at x equals c. So the sum and difference of those two functions, take one of those functions and multiply it by a constant. The product and the quotient of those two functions will still be continuous at c. And taking the function to the nth power or taking the nth root of the function will still be continuous at c. So here's a brief proof of why the sum of two continuous functions is also continuous. So to show something's continuous, ultimately we want the limit to equal the function value. So we can see that's what's going to end up happening here. So the limit of f plus g of x, well, to go from here to here, we're using our knowledge from pre-calculus. F plus g of x is f of x plus g of x. And to go to this next step, we're using the limit laws. So the limit as x approaches c of f plus the limit as x approaches c of g. And since both f and g are continuous at c, they must respectively equal their function values at c. And we can rewrite that once again as f plus g of c. We have now two important results about composite functions. So the limit of a composite function. I can evaluate the limit as x approaches c of f of g of x by pulling the limit into the composition, so f of the limit as x approaches c of g of x. I can do this if f is continuous at this limit's value, the limit as x approaches c of g of x. As long as f is continuous at this value, I can go ahead and pull a limit into a composite function. And we need that result ultimately to get this result here, which is going to help us tremendously, the continuity of composite functions. So if g is continuous at the x value b, and f is continuous at g of b, then the composition f of g of x is continuous at b. So if I think about it, if I substitute b into x, I get g of b, and we know that f is continuous at g of b, and g is continuous at b. So it's a nice result. In simpler words, it tells us that the composition of two continuous functions is also continuous. And that helps us a lot because we try to evaluate a lot of limits of composite functions. So for example, we're asked to evaluate the limit as x approaches 1 of sine of pi x over 2. So we know that as long as this function here is continuous at this x value, we can use direct substitution. But sine of pi x over 2 isn't on our list of known continuous functions. So it is, however, a composition of two known continuous functions. So the inside function, pi x over 2, is a linear function, a polynomial, continuous on all real numbers, its domain. And then the outside function, sine x, is a trig function, also continuous on all real numbers. So 1 is a real number, so that means this composition is continuous at 1. So I can evaluate this limit by using direct substitution. So I can simply plug in 1 into the x value. So I have sine of pi times 1 over 2, or just sine of pi over 2, and sine of pi over 2 happens to be positive 1. So it is a very handy tool for evaluating limits of composite functions. As long as we know this composition is continuous, we can go ahead and apply direct substitution.